Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
Welcome, everybody. And good evening from Germany. Unfortunately, I'm not allowed to come to Denver. I asked for postponing the conference for 2 weeks because then I would be allowed. Okay, next year then. I'm looking forward to see you all. This is a talk of our Back to Basics track. And that means this is something where we lean back and think a little bit and discuss a little bit about basic stuff of C++. And probably some of you are pretty new to C++. Some of you have programmed everything and want to double check whether I got it right. So who am I? I have written a couple of books of C++. I'm for 20 years now in the C++ Standards Committee. So it's partially all my fault, but not only mine. This time, I selected a couple of slides to come back and discuss Lambdas from the beginning into some details and to understand the essence of Lambdas and maybe a few tricks you didn't know. So let's look. Why do we have Lambdas? Well, assume you have a class person here, and in this class person, we have member functions to return the first and the last name, beside a couple of other stuff. We could create a vector of elements of this type, and we might try to sort the elements in this class, which would not work unless less than is provided for this type, maybe as a friend, or maybe since C++20 as a spaceship operator implemented. Anyway, we need this operator to define an ordering for persons. And it might not be there, this operation, and it might not do the right thing. We might want to sort things differently. So what we can do then is we can pass to sort an additional third parameter, which is the sorting criterion. And when we standardized C++ in 1998, the common way to deal with that was to say, okay, see, we pass a function, and this function has to answer the question whether one person should be in front of another person. So we have a helper function taking two persons. Here, in this case, we compare the last name. And if the last name is the same, we compare the first name to decide whether the first name should be in front of the second. The first person should be in front of the second person. Okay. The problem with this was that for this function, you could not specify the sorting criterion directly where you call sort. You have to do it somewhere else outside any function, because you cannot define functions inside other functions, which means you need a good name, and which might be a little bit tricky over time to maintain. So there were workarounds like a function object, but they were pretty complicated to use. So in C++11, we came with something different, and the different thing was Lambdas. And the idea was that where you need a function, as an argument, as an object, as a parameter, you specify it inline where it is. So here, this is such a function that sorts the elements comparing two persons. We don't need a name, we don't even need a name for the function, because we just pass this as a temporary object as an argument to the sort function, having no name, but the leading signal is to have square brackets there. And inside we can do the same. We can say, okay, let's return whether one last name is less than the other, or if the last name is the same, we compare the first name. With that, that's good, easy, and good to maintain. You can read and understand immediately what this sorting function does. And if we need something else, like let's sort according to a customer number, which we can also get from a person. Okay, let's do that. Let's call sort with sorting criterion, taking two persons and comparing the customer number and returning whether, depending on the customer number, whether P1 should be in front of the second person. So this was at first easier to use. And by the way, it is also better optimized than taking functions, because these local function objects, these local lambdas, have only local scope, so which and are not only declared, they are always implicitly also defined. You can't declare a lambda without defining it. So that means it's a good opportunity for compilers to optimize the code better than using ordinary functions. Now, what you see here is an application of the general principle we have when we standardize C++. We adopted the so-called STL, Standard Template Library, and in that library we defined different data structures, our containers, different algorithms, and we could combine both with iterators as a glue interface. In a way you see here, just read from one container, read from another, perform some algorithms, write to some container. Well, sort is a little bit different because we read and write the elements of the same container. The basic approach here is not an object-oriented approach. It was a generic approach. This was the beginning of the success of templates and generic programming. So, for example, we didn't have a base class for containers. We didn't have a base class for iterators. Everything that behaves like an iterator, you can use. For example, raw pointers are valid iterators. And everything that behaves like a container can be used as a range to read from. And the third thing we have is that these algorithms sometimes need help, like our sort function. And the sort function needs something to call to decide whether one element should be in front or behind the other element. We call this principle a callable, something we can call. And this can be a function pointer, a raw function pointer, or it could be a lambda, which is, as we will see, kind of an object that behaves like a function. Okay, and we have it everywhere. So we have it when we count how many elements are odd in a collection. This is my collection. My argument is a sorting criterion. Yes, I can again specify it as a function. I can then print out the result, or I can find the element, the first element in a container that is odd. And when there is one, print the value. Again, here we see that the callable is a function, but we can also use a lambda here, which is a function defined on the fly right where we need it. Okay. Now, here would be an interesting question, an interesting surprise. We would use the same criterion twice. Once we want to count how many elements are odd, and once we want to find the first element that is odd. And of course, we can have more complicated situations and more complex criteria to decide what we look for. So what we can do in this case is to say, okay, let's define an object, a variable, which is in fact an object that is our function in quotes. So that's the thing we call. That's the thing we call. And so our lambda is used as an initializer for this object. And then we have something to call, which we can pass to different algorithms at different locations. So Countif takes it and findif takes it. And here we have a function, a local function defined on the fly. Look, that we are right in some scope between the declaration of the vector and calling this algorithm. Here, right in between, we define the function we want to use twice here in this scope. And yes, this is an object. It can be used like a function, but it's an object. And you will see more details later on. Okay, first of all, please let me clarify that you can use lambdas like functions most of the time and functions like lambdas because most of the time both are things to call. There are some restrictions, we will see that later. But look at this example. We have a vector of strings. Let's sort them, okay, and print them out with the helper function. And you see them sorted, well, sorted according to the default criterion, sorting criterion, which is less than for strings, which means that if you use ASCII characters, all capital letters are in front of all lowercase letters. So that means we have all these words in front of these words in the back after sorting. So how can we change that? Well, sort. Let's call sort again and pass a sorting criterion ourselves. This time taking strings, but not comparing them with less than. So this is an algorithm calling a lambda. So the lambda has a task to compare two strings, which is two elements of these multiple elements in this vector. So how do we decide to compare them? Well, okay, let's use an algorithm. The algorithm is lexicographical compare, and it's an algorithm that can compare the elements of two different containers. You have to pass both begin and end of both containers. In this case, the container is a string. So the elements of the string are the characters in the string. So we compare character by character, S1 with S2. Now you might say, wait a minute, that's what less than does. But you can do one more thing. You can say, oh, and by the way, when you compare two characters, please convert them to uppercase characters. So here we use a lambda again. So we have an algorithm calling a lambda, calling an algorithm, calling a lambda to specify what you see here to have a case insensitive sorting. Yeah, there might be other ways to do that. Maybe not better. Maybe they are better. Case insensitive sorting is always a little bit tricky in C++. Please note that with C++20 now, things change a little bit. So you no longer have to pass begin and end of a collection. You can just pass a collection as a whole. So if we would write this example with C++20, it might look slightly different. So you would say here, oh, let's sort all elements in the collection just with less than. But this is the range version, the range library version of sort, which is in the sub namespace. It's stood ranges. And we also have there stood ranges sort for a collection that takes the sorting criterion. Same approach. We have to compare two strings, but here we use lexicographical compare to compare these two strings. So again, we don't have to pass begin and end of these strings, just the strings. And then there's another interesting thing with C++20. In the algorithms they have, they allow projections. And projections are that you can have, before we do some certain operation, that we convert or transform the element to something else. So for that, we define here a lambda, a local object that says, oh, convert the character to uppercase character. That's just on one line, a lambda. And we pass this here as the fourth and fifth argument. So you have to read it that way. We have a string as first range, string as second range. So from there, we take the elements. And then we compare elements of S1, so characters of S1 with the characters of S2. In general, we compare with less than. That's a default sorting criterion. You could also use a lambda here, but we have a predefined sorting criterion for that, so we can use that. By the way, if you're missing here angel brackets with class template argument deduction introduced in C++17, that's no longer necessary. You just have to create a criterion to perform less with the characters. But before we compare them, let's both the character of S1 and the character of S2 convert to an uppercase character, and you get the same result. Again, it's a question whether you want to program that way, but you might see some interesting things. If you just see how this works, it's a clear description of what's going on, instead of just code combining multiple statements and having inner expressions, etc. So you can compute easily that way. Please note that it's not a performance penalty, because more or less everything here is inline defined lambdas anyway. So if you look at generated code generated from compilers, it is as good as we would pass to sort directly the command, compare the characters of the string after converting them to an uppercase character. Again, lambdas help here to have better optimization. In C++14, we introduced something else. We introduced generic lambdas. So you could say, oh, I don't care about the type of the passed argument. I take everything as long as it compiles. So here we have a lambda, an online defined function we call twice. Well, we have the lambda here, and with this lambda, we initialize an object. We can call twice for an int, twice for a double, twice for a string, and twice for a string little. Well, wait, what the compiler does, it uses this function and compiles it for an int, x being an int, a double, a string, or a string literal, and that will not compile because you cannot compute plus for two string literals. That will not compile. But this is compiled for different parameter types, so multiple times. Again, don't worry about code bloats because all is expanded inline. You will not see function calls at all in the generated code. So let's iterate over the elements of a collection and print out the elements twice, as long as plus is defined for the elements. This code will will work in generic code as generic code. Good. There was a question I should answer here, which is why am I not using toUpper here directly? Why am I using a lambda? Well, there are two answers of that. The first is I want to demonstrate you how you can combine things. And the second is std toUpper is a C function, for which combining things together like combining building blocks, you run into problems with generic code. And in this case, it really does not compile to just pass std toUpper, just this, instead of toUpper. So you have to do it that way. That's a problem we have because it's a C function. It's not a general problem. We could also use here helper functions. Okay. So what else to say? Well, a few other things you might not be aware of. I will answer other questions later because some of them I saw I will answer anyway, I think, with following slides. So the first thing is, if your lambda has no captures, that is, it has no arguments here, we will talk about that in a moment, then it can be used as an ordinary function pointer. You can even pass it to a C function expecting a function pointer. So you can see it here. there is a C function, a standard C function called x@exit. You can register a function taking no argument, returning void to do something whenever the program exits. You can pass a lambda there. In that case, you don't even have to pass any parentheses at all. So you could directly, after the two square brackets, continue with the opening curly brace. And there's another thing you can do with lambdas that have no captchas, that are empty here, which is you can use them as sorting criterion or hash function type. Well, this is really good, supported since C++20. So look at this. Define your own hash function. And that's interesting. You can use a generic lambda here. Yes, you can take an object of arbitrary type as long here you have some way to use this object to compute a hash value, whatever the code is there. And then you can declare an unordered set of maybe some type. I use here my type. And then you have to pass here, well, an unordered set needs the type of the hash function. So you pass decal type of the lambda, because lambda is the hash function. Well, is the callable that can be used like a hash function. With decal type, you get its type, and then the container will create an object of this internally to compute the position of the elements in this unordered set to have the elements placed and organized correctly. So these were the basics. Let's see, what time is it? Oh, we are good in time. So lambdas are better functions. Well, I gave you two arguments already, but these arguments are a little bit fuzzy. I mean, I said, oh, you can define them locally, and they might be better optimized. Well, in non-trivial cases. But there's really benefit, something lambdas can do, which ordinary functions can't. They are functions with a state. And you can specify the behavior at runtime, the behavior of the function at runtime. Both belongs together. So let's see what I mean here. Assume you call Countif, one of our algorithms. So std Countif, there should be, just I skip std to have enough room. So let's count how many elements in C are less than 7. So we can pass a lambda here, and we can compare whatever we get with 7. Could be int, could be auto here. Okay. That is, we use a function as a criterion to count how many elements fulfill our predicate, a Boolean condition. If we want to compare with A, we need a another function. We can no longer use this function. We cannot add the parameter here because it's called by Countif, and they give me only one element. So we need another function here, less than 8. So for all the different values, I need another function? Oh my God. But it's even worse. So think about, you want to count how many elements are less than a given parameter max. So max here comes at runtime, and you can't define a less max function at runtime. Well, yeah, you could introduce a global object. You didn't say that. You didn't even think that, okay? So no, you can't do that with ordinary functions in a useful way. So you can use lambdas instead, and with lambdas, it's no problem. So yes, we can call Countif, say count how many elements are less than 7 or less than 8. But the interesting part is this one. And that looks like this. So you call foo with the parameter, and here you pass a lambda capturing the maximum. And that is something functions cannot do. You create a function on the fly. The function has the behavior to compare all the elements with max. Max is computed at runtime. So you compute and describe and define the behavior of this function at runtime. And then you can use it like an ordinary function. This is a function created on the fly, and the function is an object that stores max in its own member, as we will see in a moment. Here's a complete example. Vector of int, maximum, Countif. We have to capture maximum into the lambda. And now we count according to the value that was computed at runtime here. So lambdas have two types of parameters. Parameters for the behavior here, parameters when they are called. Yeah, and that is something that goes beyond ordinary functions. And that's very, very powerful. So you can, again, use generic code here. So you can say my parameter here is auto or const autoreference if you don't want to copy the elements. Yeah, will work. The power of this feature may become clear if you look at this example. So let's process an invoice. We have a parameter here. The parameter is an invoice we get from the calling side. So what we do is we have to find out what is the amount of text to add to any item in this invoice. So let's call a function getText, returning a double. It could be auto here. And then we do the following. We create a function that adds text. We create a function on the fly, here locally, that adds the text that is necessary for this invoice. Maybe in the US, a state-dependent or even town-dependent text has to be added. Or, I don't know, in Germany, we have two different text values. Don't know. Maybe you compute the text depending on country, on the town. You can also think about this being discount for a specific customer. In any case, you create a function that can add or subtract or multiply with the discount or the text you have. And then you use it like a function. So let's print out the sum of the invoice plus text. Let's iterate over the items in the invoice, add text for each value. Well, this should be item, not value. That was something you have to find. Okay, and maybe we go over all the elements in the invoice and add text to each element, reading from the same container and writing to the same container. Whatever is possible and can be used. So we can slightly modify this example because I told you already, plus text is not a function, is not a function pointer or something like that. It's not that this function can only be used here inside. So we can do the following. We can say, okay, for this invoice, create a function that can add text and return it. So you return a local function object that adds text to this invoice. Look how this can be used. So you might have two invoices. You might have a collection of invoices. You create for each invoice a plus text function, and you use it later on. And these different functions can coexist simultaneously. Here you see that these are really objects that have a state. So what you create is an object where the current text is stored. And it's also stored here. It might be the same, it might be different, and you can use it here. Again, please note, this might not be you ask for text of an invoice. This might be the discount of your customer. And for each and every customer you have currently in your system, you can create its own function to compute the discount, which especially is important if while the customer is buying things, that the discount doesn't change. It should be stable over the session of the customer. So you put it in a helper function. Yeah, that's what you can do because this is an object. Okay, lambdas are function objects. And now it's time to look behind the scene. So if you specify a lambda like this, if you define a lambda here in the gray area, whenever a compiler sees this code in your source file, whether it's in header or in CPP file, it creates a type. A type for objects you can use like a function. And that's what we call a function object. And so the compiler decides by some name to generate this type. There's a default constructor, and here's an operator parent, which is a function call operator, which means object, you can be used like a function. Having the same parameters, the same behavior, same return value. Yeah. The type of this lambda is the type of this class. And we define this, the closure type. The name of this is the closure type. If you ask the type system, the type traits of C++ about what is a lambda, the answer will be it's an object of a type, of a class. It's a class object. So yeah, each lambda is only a shortcut for this. And the compiler decides about the name. So that's why I wrote here something like that. The compiler has to use some useful name depending on its internal programming logic platform, maybe the location in the file, usually something with a hash value inside, whatsoever. That's not all. The compiler creates this type and creates an object of this type. So where we have the expression, where we define the lambda, we create an object of this type. And that object is here then used to initialize it. And that happens all the time when you create a lambda, when you define a lambda. The compiler creates type, a class, and creates an object of this class where you find the expression. And now if you do something with this function, for example, you call add, and you want to add 17 plus I. That means you have an object here, and you are using the object like a function. So what is called here for add? This operator, this generated operator is called with the two parameters. So it's the operator, use me as a function, empty parenthesis, and then inside the parenthesis, the parameters you pass. This was something you could do to get the same behavior before C++ 11, but people got crazy about that, at least if they were not used about that. So these are function objects. And what a lambda really is, it's just a very simple way to create a function object. Here's another example. Let's find in the collection the first integer that is less than a minimum, or less or equal a minimum, and that is greater or equal a minimum and less or equal a maximum. So that is between min and max. Once again, you learned the rule. The rule is create a type and create an object of this type for the expression where the lambda is defined. So this is an object. In this case, we capture two types of information. We capture a minimum and a maximum into the object. And here you see that it's really an object that has internally a state, because internally we store the minimum and maximum we capture. And then later on, when we use this, when findIf uses this object as a function, it uses the internally stored min and max. So here you see findIf, a little bit simplified. So findIf takes begin and end iterator to iterate over the elements and something to call, a callback or a call level. And this to call might be a function or function pointer. Then you call it the usual way. But this code, if this is an object of this type, this is what we pass in, an object of this type. If we then call this inside the algorithm, what we really call is, we call for the object, the operator use me like a function. And the value passed here is the current value of the iterator, so where the current iterator points to. So, and what happens if we have generic lambdas? So you have a lambda taking two outer parameters and computing the sum. So doing something like plus, again, create a type, a class, where you have a corresponding constructor here capturing nothing, so default constructor. And here, now we have parameters for the function call saying this could be an arbitrary type. And for that, we have templates. So the generated type is a type that is a function object type where the function call object call, the function call is a template, a function template. And then again, you create an object of this type and assign it to plus. So here we have an object of this type. And then we can call plus for a double and an int, or plus for a string and a string literal. And for example, if we call plus for a double and an int, that means we use this object. So an object of this type, calling the function call operator. But we have to find out what are the template parameters. Well, the first one is a double, the second one is an int. So what you really call is this. You call for plus, the operator use me as a function, instantiated for double and int as types T1 and T2, and pass parameters are 7.7 and I. By the way, you could write that manually. Don't do that. Don't do that. But you could, and it would compile. Okay, that's the secret of lambdas. If you have understood the last 3 slides, you understood lambdas. Lambdas are just a shortcut. And you know what? A lot of programmers hate function objects. That was our experience. A lot of programmers hate templates because that goes beyond what they usually learn. It takes a while until you get used to it. And you're always nervous if you use templates, a lot of programmers at least. Well, for them, we just have introduced a new syntax. They have absolutely no problem to use that, but they have a lot of problems to implement that themselves. This is a shortcut for this. That's all. It was a big success because lambdas are used a lot. We see that in each and every application programmer's code. It's easy to use. So there's a difference you should notice. Look at this. This is a lambda, a generic lambda. give me a collection, I iterate over the collections and print them out. And this is a generic function. Give me a collection, I iterate over the elements and print them out. This looks like being pretty much the same, but they are totally different. So this is a function object. This is an object where the function call operator is generic, is a template, it's a function template. This is a function template. The function as a whole is not an object of a type. It's a function that is has to be compiled the moment we know where it's used for. There's a difference in use for them. So for both of them, you can use to print the elements of a vector or whatever you can use to iterate over a collection. So this is a vector of int, print the elements in the int or in the vector with function template or with a lambda, works fine, both. But there are differences. The differences is this. First, this is a function template. So in a function template, you can explicitly specify the type of T, the type of the template parameter. So this is fine. You can say, oh, here we pass here a string literal, and let's print the function as a string. Yeah, for whatever reason. This will not compile with a lambda. A lambda is not a function template. This is simply not possible. Will not compile. But there's also something better with lambdas than with functions. Look at this. If you have to pass a function to some other function, so you say, hey, call me this function with this vector. One example is std async or std thread. And I think there was a question in the Q&As asking about, can we combine async and lambdas? Yes, of course we can in any way. And think about this as async. And we pass here something, yeah, could be a function, could be a lambda. Async and thread take callables. So, however, if what you call is a function template, this will not compile. Because at the moment we call this function, we have to know the type. But the type we don't know until we call this function for actually this element. And here, from this declaration, we can't associate, combine these two informations so that it compiles. And so you have to pass something like this. Take the function template and pass and explicitly say, well, type T should be the type of the vector we are iterating over, and then pass a vector. That will work. For lambdas, this is not a problem because the lambda is not an object that is templified. It's that the function call operator is templified. So you can pass here lambda and it will work. And that is, by the way, one reason a lot of people, programmers, prefer now lambdas over templates. Yeah, because this is additional flexibility. And for all of you who have heard a little bit about C++20 already, look at this area here. In C++20, you can write it that way. Yes, we allowed in C++20 auto as a function call parameter, but this is still a function template. It's just another syntax for that. The same rules apply. This is not a lambda. So if you declare it that way, still you can explicitly specify the type of the element of the thing here, but you have to pass the type if you pass it to something that will later call this print function. Okay. So I will answer, there's so many questions now. I will answer them at the end, I think, and we'll first finish, and I hope we have a few minutes left. A few things, just some final words about capturing. So you have seen this example already a little bit, where we said, let's initialize a minimum and a maximum, find the first element that is between the minimum and the maximum. The rules are all the values captured are captured by value, but they are read-only. So yes, this is a local copy of the elements. And that means this lambda can even be passed around. The lambda contains its local copy of min and max. And I think that answers one question about the text example, whether we can return the text, the object to add text. Yes, because we captured the text by value. Don't capture it by reference, then it would be a nightmare. So the rule is like this. You have a prefix, you define the lambda. This is the moment the lambda creates the copy. Remember, here we call the constructor of the generated closure type. And the constructor creates an internal copy of this prefix. So here the lambda now has its own prefix. So any modification of the prefix will have no impact on the defined lambda. So if we later on use the lambda, it will use the prefix we had when we defined the lambda. Okay, you can capture by reference. If you pass with an ampersand, you can qualify a specific value to capture it by reference. In some code, I often see just this, which would mean everything visible outside the lambda is also visible inside. But be careful. If then this is used somewhere externally and you pass this lambda to there, then you might have a problem. It's like always having a problem when referring to something that is no longer in scope. With C++ 14, we also introduced something like this. You don't have to capture things that already exist. You can create them on the fly. So this is like the text function before. Let's create a discount function. And what do? Well, we initialize here the discount as a result of calling discount for a customer defined before. And with this discount, we create a function, local copy. This is a local copy. We create a function that can, to an item, compute the price. This should be the price, not the prince. Very nice. Okay, and we should compute the price, but maybe there's a good example for prince, and then multiply it with the discount. And this can be used like this. There's an interesting trick. You can't capture by const reference, but there's a trick. You can capture by reference and initialize with the past value converted to a const object. So that is coming from C++ 17, and that's a workaround. I still think we should introduce an opportunity to declare this with const reference, but okay, it's at least possible with that. So we come to the last feature I want to present in this hour. Look at this. Lambdas create a local copy of what they capture. This local copy is read-only. So if you try to modify it, that's a compile time error. So here we have a local copy. Maybe we have previous pref defined formally, or maybe it's created new here and initialized with 0. Doesn't matter. We have here something that is part of the state of the function object of the lambda. So each lambda has a previous value. You wonder what the type is? Well, it works when you capture like having auto in front of this. So it has a type of what it had from the outside or how it was initialized. So here it would be an int. So what is the idea? We want to implement a lambda that returns true if we get a different value from before, from the previous call. So the answer depends on what was the previous call. The way to implement that is pretty easy. So let's check whether the previous value, initially 0, is different from the new value. Then we change. Then we have to store here the new value as the previous value for the next time. And then we return true or false, depending on whether it changed. This will not compile because we don't allow you to modify the local copy. You might say, wait a minute, that's a local copy. Where's the problem? Well, that's to protect you. That's to protect you. And you will see in a moment why. First of all, you can fix this problem. You can say, oh, it's mutable. This lambda is mutable. And that means it can change its internal state. It's no longer stateless. Stateless does not mean it doesn't have a state. Stateless means the state is always the same. We have that terminology in different areas of IT, like in service-oriented architecture, for example. So stateless means you can be sure if this function is called with a certain value, it will always give the same result or have the same behavior. Stateful means you never know. So what happens might depend on what happened before. And that's something we have here because what we return here depends on the value we had before. So we have to enable statefulness. And what we do with that, we enable that this assignment is allowed and compiles. So now let's use that. Vector of int, copy all the elements from this vector that changed. So we're using this lambda. So where the new value is different from the previous value, the first value is 0. Okay, so 7 is different, 42 is different. Oh, that's not different. That's filtered out. 0, 3, 3 again is not copied, and 7. So this is the output of this call. So now I can explain you why we by default don't want you to do that. Because you run into a problem if you have a lambda like this. The problem is easy. Tell me what is printed here. What is printed here? Now, I do the same again. Because note, we ended with 7, and then next time we start with 7. So this looks like, yeah, we have different behavior. And that's a problem you get when you have stateful lambdas. If they are stateless, always with the same value, same result. So this is not the case here. And the answer is, by the way, no, this is not a problem. It will again start with 7. Why that? Because this depends on how we deal with this lambda, with the callable to call. So because you have to look in the declaration of CopyIf, and you will see that all algorithms take their callables by value. So they create their own internal copy. So we have a lambda initialized with previous is 0. And then CopyIf creates a copy of that. So we operate on a copy of change that starts with the value 0. And here we still have the original object and copy it again starting with 0. The thing we do here with the lambda does not impact the original object because it's passed by value. Same here. Only if you call change 7, so only if you in the original object say, oh, my previous value was 7, then suddenly the next 7 will be detected as, oh, that's not a different object, that hasn't changed. So let's here, skip it. And now you know why. Without mutable things, situations like that cannot happen. If you have stateful objects, you have to be very carefully to know when objects are copied and when are not. Okay, so that's it. Okay, somebody got already some ideas for great pub quizzes here. Yeah, I'm pretty sure, as with any feature, I read it just in the chat. So let's see the questions we have and come up with some answers. Where do you draw the line for choosing lambdas or free functions? Lambdas only when they're callable, because I've seen some functions really cluttered by lots of lambdas. Oh, when do I prefer to have small functions and large functions? When do I prefer to have a single statement or multiple statements or multiple function calls? That's a design question. It should be maintainable. That's all. And of course, lambdas should usually not be that long because they are inline and have local scope, something like that. I don't have a clear guideline like that. How expensive is it to declare a lambda? Could it cost slowdown if it was locally declared in a function that is called often? No. Lambdas are optimized away. So it's more likely that the function call is optimized away. So if you declare lambda locally or use it directly locally, that's definitely not a penalty against raw functions. Definitely not. It might be even faster, but don't count on that. That's little improvement, and you need certain examples for that. Is it cheaper than a function call? Yes, a lambda may be cheaper than a function call because lambdas can be better optimized because they are always defined when declared. So they're always inline, and they don't have to deal with the fact that from some other place, somebody might call this function. So because it's only locally visible. What happens if we write the same lambda in two different places? Will the compiler create two different classes for each of these lambdas? Yes, that's right. If you have this changed here, and you use this lambda, and you have a second time this line, with change to the same content of the lambda, you have created two different objects of two different types. Of course, the objects should not have the same name. So you can use type traits to compare the types, and they will answer that you have different types. You can copy a lambda, then they have the same type. But if you have two different places where a lambda is defined, you have two different types, which means if you have a lambda defined in a header file, and this header file is used in multiple translation units, formally in each translation unit, you have compiled a different type. On slide 11, can you pass directly? Oh, we had that. Do lambdas exist on the stack? Yes. Everything you have seen exists on the stack. It's just we create an object, like we create an object. We create an object and initialize a member. All you have seen is to create it on the stack. So you might see my email in a moment or my Twitter account. I give you a task. Create an object, a lambda for me on the heap. Please do that and send me the solution. That's the interesting part. How do you create the whole lambda on the heap? Okay. Does lambdas type always have to be auto-to-be platform independent? Yes. Well, not only to be platform independent, it has to be auto. End of discussion. Because the type is, you don't know the name of the type. The compiler decides. And that's it. There's a way to declare it a little bit weaker, which is to use std function. But this is only a wrapper around the real type. So each lambda has its own type. You don't know the name. When you need the time, use decl type. I often find myself using lambdas with reference captchas to split and name subprocedures out of main parts of large functions without thinking much about passing state around. Code readers don't seem to like this much. As a member of the committee, what do you think? Well, I tell you what, we in the committee have different opinions about style guides. So that can be interesting. What happens if I give you an advice? I would say that if you have a local function and you say, I just want to have everything visible in this local lambda, and I would have to pass all the individual parameters one after the other, then just an ampersand is fine. I know that some people don't like that. And I would prefer, if you just have one or two arguments, that I would then use ampersand with the name of the arguments. And please never use the equal sign, which means capture all by value, because that means that you don't realize that you might accidentally capture a vector of strings. So don't do that. But with reference, at least for performance reasons, it's okay. If your lambda is used somewhere else, don't do that, because you might refer to something that is no longer visible when the lambda is used. Could you explain the difference between capturing this and capturing star this? Yeah. The point is, there's a special rule in C++ saying, if you capture star this, we copy the object of the member function you're calling this, lambda in. So if you capture this, you create a copy of this. Remember, this is only a pointer. It doesn't, by the way, it does not matter whether you capture this by value or by reference. But the point is, then you have still the original object. But think about, you are in a member function, and that member function starts a thread. And then this thread, you need the object you are just doing something for. Then you want to, if you create a copy and you want to pass a copy of this object, please use star this, because star this creates a copy of the current object. Are there restrictions on whether and how often standard algorithm can copy callables internally after they take the original callable by value? No, and that's a good point. We have algorithms that in the middle of them working, copy the callables again. I have it in my C++ standard book, 2 or 3 examples for that. Send me an email and I give you the link. The point is, yes, we don't guarantee, unless the algorithm specifies it explicitly, how often a callable is copied. It could be that this object change is internally, after doing 3/2 of the processing, doing a copy again. Well, that will not copy. Well, I hope it's not copy. It's not happening with copy if. So then this would be a very interesting example. I know that there are algorithms like that. Was it remove if? Something like that. I don't remember. But send me an email and I'm happy to answer that, or I can tweet it later on. So we are close to having time is over. So let's see whether I see some other interesting questions. Capture by value, lambda is stateless. Wouldn't capture by reference. Captured by value, lambda is stateless. Wouldn't captured by reference, lambda be stateful? Yes, of course. I mean, then the behavior of the lambda always might depend on changes in the outside. Yes, you're right. How did I get writing books? Well, when my first child was born over Christmas time, I had too much time and I had to write. So I took the task. What are the scenarios in which you can only use function pointers but not lambdas? There are no easy answer I have in my head now. And it's 6 minutes over, so that's a trick to say, oh, I can't answer that question anymore. But I'm happy to be available in the ballroom in the Gather Town. So I will be there. And thank you very much for your attention. And if you have more rooms, more asks, yes, you have to go to the room for track E. We are in track E, and there should be a link. Maybe somebody can post the link here in the chat before we close it. Thank you very much. Enjoy the conference. And by the way, If you want to read more from me, the new C++20 book is out, and not complete, but it's out. Read it. Cheers. Thank you very much.